The equipment we use at UC Berkeley for running constant rate of strain consolidation testing was designed by Clarence Chan here in-house about 40 years ago. And it was custom designed to test relatively large specimens. So we're going to be working with a consolidation ring that's about 10 centimeters in diameter, inside diameter, and about 2 centimeters tall. And that ring needs to seal against a base plate. So we're working with this very large stainless steel base plate. It weighs about 30 pounds. And the O-ring seal you can see here is what's going to seal against the bottom of the ring so that we can isolate the pressure at the bottom of the specimen, which is detected through this porous stone in the center, separately from the pressure in the chamber that's going to be around it. So once we get a specimen trimmed into this ring, we're going to place it here. We're going to try to make sure our drainage line, which comes out through this black valve, is completely saturated with water. In order to keep that good seal, we're going to bolt down this ring on the top to the base plate to maintain good stress across that O-ring seal. And then the chamber that we're going to fill with water and then apply air pressure on the top is here, plexiglass. Then the top has a large diameter stone, as you can see, attached to the piston, and a port at the top for applying air pressure. So we'll be placing that on and gently letting that top stone fit right into the center of the ring. Bolt it down and we'll be ready to go. Our undisturbed samples in the field are stored in a high moisture room, and we seal them with plastic at the top to make sure they don't dry out or absorb water with their capillary stresses. They have an inside diameter of about 12.5 centimeters, whereas we want to trim that down to a 10 centimeter diameter ring, and that's intentional. The soil around the edge of the specimen or the sample is most likely to be disturbed by the actual insertion of the sampling tube in the field. So we want to extrude a slice of soil that's taller than the ring that we want to trim the soil into. That's about 2 centimeters tall, so we'll extrude something around 4 centimeters, plus or minus a little bit, doesn't matter too much. It's important though that we also push the soil out of the top of the tube. Remember, there's a cutting edge on the bottom edge of the tube where the diameter gets a little smaller. We don't want to force the soil out through that. We want to keep the soil moving in the same direction that it entered the tube. So I'm going to put this on the top. When the samplers are really full, sometimes it's very hard. There's a lot of force required to get it out. We have to use a hydraulic press. But this tube doesn't have a whole lot of soil in it right now, so hopefully I can just move this statically. So, taller than we need to fill this ring. And we're going to use a wire saw to cut this slice off. Put it on a glass plate. So, this is just a regular thin piece of wire, has no teeth or anything like that. It's very dull sort of a saw, but it's good for trimming through soft clay soils. I'm slicing a little bit as I go left and right. I'm going to support the back of the cut with my fingers so we don't break out a big chunk. Great. And then bay mud has silt seams in it. We always want to be careful not to ever put it in tension. So we always want to have a little bit of compression on the soil. It's a saturated clay, so isotropic compression is very safe. Nothing's going to happen to it with that. So to do that, I'm going to squeeze from the two sides and twist a little bit and put the soil on the plate. Now before we start trimming the soil down to the right size to fit in the ring, you want to make sure we're ready, because once the sample's in the ring it becomes much harder to measure the ring. So it's very important to get a precise inside diameter. They're all a little bit different. Precise height and mass. We're going to weigh the entire system with the ring and the soil at the end of trimming. We want to be able to subtract the ring mass in order to be able to know how much moist soil we have in there. While we're looking at it, the white material on the inside here is Teflon. So it's a composite ring with stainless steel on the outside and the ring of Teflon on the inside. That's there to prevent or minimize friction as the soil is consolidating along the side walls. And the stainless steel, of course, provides the rigidity so that when we push down on it with a large stress, the ring doesn't expand. So the trimmer we're looking at here is a homemade device. Essentially, it's a platform on a bearing system, which is on a table that's threaded into the base. So if I turn the whole base this direction, the entire column lowers downward. And as I turn the base this way, the whole column moves upward very slightly based on the pitch of the thread. So we want to start with the center post right up level with the top of the ring, so we have a nice flat surface there. And then we're going to take our soil slice and we're going to twist it off, slide it off, keep it in compression, use the mass of the soil, self-weight, to provide the compression. Don't pick it up from this side or we might find a silt seam or it would just fail. And then we're going to just place it down on the ring. And the outside diameter of the ring is about the diameter of the soil sample. So we're going to trim away the excess around the sample until it's just the right size. And we're going to use two tools to do that. The first one of them is a very fine wire saw. And we're going to just use this to get rid of most of the extra material. So the outside of the sample has now been trimmed down with the wire saw until we've reached the point where we can see a significant amount of that white Teflon ring all the way around the specimen at the bottom. We've tried to keep the taper in as we go down with the wire saw so that we don't get a sample that's too short up near the top. And now we're going to switch over to a different kind of a trimmer. So it's a very simple sort of a trimming jig where the trimmer is, active end is right here, this point. It's hard to see probably there, but it's sharpened a little bit. And there's a notch of a very precise distance, which matches the distance from the outside of the ring to the inside of the Teflon. So as long as I keep this tool horizontal, it's impossible for the point of this trimmer to reach to the inside of the white Teflon ring. So we're going to use this almost like a scraper. We're going to kind of gently remove the soil. I don't have to push it all the way in when I start. Gently remove the soil around just the bottom of the material. That curved nose on the trimmer means that the point that's reaching in the furthest and making the diameter the smallest is right down at the very bottom. Okay, so I'm going to be keeping the handle horizontal. I also want to keep my hand ahead of the cutter tip so that, I'm going to exaggerate here a little bit, so that the tip is pushing the soil toward the center. Right? if I let my hand fall behind, I could reach a point where the tip of the cutting tool is sort of pulling soil out, pulling out chunks of soil from the specimen. And like we said, that's tension, that's a bad thing. We want to keep a little compression, keep squeezing the soil toward the center of the ring as we do this trimming. Now, if you're left-handed, you can work on the other side. You should always pull the tool toward you. I'm right-handed, so I'm working over here. It gets a little awkward to trim on the back side, so to turn the sample, I want to be really careful to always turn from the top. I can turn this ring any way I want without changing the height of the system. I don't want to lower the whole table until I'm really convinced that I'm ready to lower it and make it shorter. So I'm just going to work my way around with this trimmer, turning the sample, keeping the soil in compression, scraping away soil with the tip. So I've removed all the soil that I can reach essentially with this trimmer, and since it's designed to be just the right size, that means I should have little to no soil now between the diameter of the inside of the Teflon ring and the soil itself. So now I'm actually ready to start lowering the soil down into the ring. And of course, because of the curvature on this tool, as soon as I lower it a little bit, the soil is going to actually be a little wider, and I'm going to have contact again, and I'm going to need to trim away a little more material. So we're only going to lower it a little bit at a time, and to do that we want to apply a little bit of pressure on the top with your full hand, not leaning on it real hard, but just guide it. And I'm turning now the table at the bottom, lowering the whole support system down through the threads at the bottom, and I can see a little bead of soil now around the edge, and that's where I'm starting to contact or push away some soil. So I want to stop there and resume my trimming with this trimmer. Maybe once or twice around is all it's going to take before it's ready to lower some more. So I'm going to continue with that, and rather than video the whole thing, we'll just do some time-lapse stills maybe of how it looks as it's getting lowered through the specimen ring. So how do we know when we're done? If we remembered to measure the thickness of the slice of soil before we started, then we can always check what the current amount of soil sticking up above the ring is. In this case, it's about 1 centimeter. This is a little curved, so it's a little hard to see, but it's about 1 centimeter. And it started out about 4 centimeters with a 2 centimeter ring. So we have about 1 centimeter on both top and bottom. So this is a good place to stop. We always want to be sure to trim some soil all the way through the ring and then trim it away, because the initial part of the trimming is always the most disturbing. It's more likely to shift around a little bit and be have some gaps around the ring or something like that on the bottom side. So we want to trim the soil all the way through so we can cut some of that away. So this means we're done with this trimmer, and what we're going to do is slide this back and trim it up. So we need to cut the specimen flush with the top and the bottom surfaces of the ring. So to do that, we want to stand the sample on its side. We're going to use the wire saw again to pass through and cut the base cap. You can see is still attached to the soil that was at the bottom. We're just going to slide that wire saw through. All the way to the bottom. And peel that off. Pretty nice cut. Do the same on the other side with what was the top of the specimen. Take the wire saw, smooth cut. Top is cracked, that's okay, we don't want that part. Surface looks okay, we've got a little extra crumb there, but it's quite likely when we use the wire saw that actually, because the wire is flexible, we don't have a really planar surface there. So the last treatment then is going to be with this rigid blade. It's basically a strip of rigid stainless steel with a sharp cutting edge on one side, and we're going to use that to really create a planar surface across both the top and the bottom of the soil. So we're just going to cut that, use the ring as the guide, glide across the top there, scraping away a little bit of soil so that the actual ring volume we know is full of soil. And we're going to do the same on the other side. In order to switch it, we want to stand it up and slide the specimen relative to the plate so that we don't have something stick. We'll use the blade on this side as well, keeping it down in contact with the ring on both sides, sliding across. And we're removing a little more soil on this side, as you can see. So we want to know that our soil mass is actually, as precisely as possible, filling that measured volume. Great. So then, very important, we go get the mass of this, clean it off a little bit. Actually, it's good to clean off any extra soil around the Teflon or the stainless so that we're measuring soil that's inside the ring, right? And also we're going to want to see exactly where the white edge of the Teflon is when we're setting up the consolidation test equipment. So it's important to not obscure that edge with some of the mud. Okay, and then we're ready to set up, once we weigh it, we're ready to set up the equipment for consolidation testing. So in order to set up our specimen for the constant rate of strain consolidation test, we're going to work with the base plate, and before we put the specimen in, we want to make sure that the drain line between the bottom porous stone and the valve is saturated with water. So what I'm going to do is connect this reservoir, which has a water level down here. I can apply vacuum to the top of that. I can de-air water and control vacuum those specimens with this. But for now, I'm just going to use it as a reservoir of de-aired water, so that as I raise the head by lifting this up in the air, we should get some water flowing down through the valve, underneath the bottom, and into this porous stone. So here comes the water around here. If I was going to be super thorough about this, I would probably pre-saturate this stone by boiling it in de-aired water first. But mostly I'm concerned about having the drain line full of water and not air. So this should be fine. Then once I'm convinced that there's no more air bubbles coming out, I'm going to close the valve so that remains saturated. I can remove the connection and we don't need this reservoir anymore. We don't want to flood the soil though with free water either, because that would relieve the capillary stresses and we'd have a much harder time measuring the maximum pass pressure. So we're going to towel that off just moist. Then we're ready to take our specimen. There isn't really a top or bottom. Both look fine. So we're going to take this side, place it down against that O-ring seal. And the other parts of the system. This is the rigid plate that enforces that face seal between the O-ring and the bottom of the cell, so that our excess pore pressures at the base, U sub B, are not affected by the water pressure in the chamber. Sealed away from that. And these parts are all, of course, made to be centered in the middle of the cell, so that when we bring the top over with the piston and the top porous stone, those will just fit down nice and smooth inside the ring. So we'll put the chamber on. That also seals with an O-ring. And then the top. Relatively simple. Again, this is the port for the chamber pressure. We'll use that to control what the pressure in the water is around the outside of the specimen. So similar to a incremental test, we are going to submerge the specimen in water from the top, but unlike an incremental test, or at least most incremental tests, we're going to be able to apply pressure to the water in the basin, and that's essentially like back pressure that we would use to saturate a CU specimen or something like that. So we have more confidence that our specimen and our system is going to be saturated with this device than we would with an incremental test. I'm going to gently lower this down onto the soil surface. We don't want to touch it after that. We'll set up the LVDT over on the loading frame. So here's the CRS consolidation cell set up in the load frame. We have the drainage line connected now. That one that we were sure to saturate is now linked to a tube that goes over to a pressure transducer mounted on this panel. And we can close the drainage line beyond that transducer to make sure that the system is undrained and still measure the pore pressures at the base of the sample, which is so important. We have a load cell at the top mounted to the frame. Just like in the vacuum triaxial test, the system is going to slowly push. I'm not in contact yet, so I want to get close. But the system is going to, when it's turned on, very slowly move the whole table, including the chamber and the specimen, up against the load cell. So the table moves at a more or less constant rate, and we measure the resulting load, as well as the displacement with the linear variable differential transformer, LVDT. That's basically measuring the change in position between the loading rod, which passes right through the top cap, and the top of the rigid chamber here. So it doesn't matter how much the load cell squeezes, we're not going to measure that compliance in our system. So the first thing we would do is apply a small seating load. That area of the specimen is about 80 square centimeters. Some are a little bigger or smaller, but about 80 square centimeters. So if we apply 8 kilograms of seating load, that's 1/10 of a kilogram per square centimeter, which is about 10 kPa, which is large enough to make sure we have good seating between all the elements. The porous stone is not sticking up on some little bit of soil or something like that. But it's not so large as to actually deform the soil in any significant way as long as the maximum pass pressure is significantly higher than that. So we would apply that seeding load first, then we'll add water to the chamber to submerge the whole system. And then after the system has reached equilibrium, we'll close the drainage valve on the system and start the test by very slowly moving the table up against the load cell at a constant rate of strain, hence the name. Here's an example of the data we may see when we run a constant rate of strain consolidation test. The white line, which is very flat, kind of behind the others, is the LVDT displacement in millimeters. Not a whole lot of change because of the scale, but it's linear with time. These are all histories, so they're all as a function of time here. The green line on the top is the load response. So we see a very stiff response initially. It starts to bend over, probably going past the peak, past maximum pressure, at which point we decide to do the unload and reload part of the test. So we reverse directions of the table. Instead of having the table move up against the load cell, we now have it move very slowly down. And of course the soil responds by exerting much less load against the load cell. You can see that trough then stops when we stop the unloading. There's a small flat portion while we wait a little bit for equilibration. And then when we reload the specimen, of course, the sample is significantly stiffer. The load goes up faster with time because we've just been up to that stress before, right? The specimen has no disturbance or anything relative to that previous load just an hour before or so. And so we see a very stiff response and a very clear bend over in the load where the soil becomes softer again, because once again we've exceeded the maximum past stress, the maximum past pressure. And then as the load continues on out to the right, we can see that it's actually curving a little bit. It's convex up, and that's because this is a linear scale. We'd expect the load with time to be kind of log linear, but of course this is a natural scale for time, and so it's going to be convex up. It's going to get progressively stiffer as time goes on. The third line shown here, the red line, is showing the excess pore pressure, U sub B. And so when we are first applying load, we get small positive pressures. They look like a decline. The polarity is backwards in the system because it's an effective stress transducer. But when the load is initially going up, that red line is dropping. That indicates a drop in effective stress or an increase in pore pressure at the base. You can see mirroring of the unload reload, right? When we lower the load, the effective stress rises rather rapidly, and then it drops again gradually as we increase the load out to the right. So those are the three parameters that we measure during the constant rate of strain consolidation test. Here they're in terms of kilograms, millimeters, and pressure in kPa. So we need to do some data processing and reduction to interpret the test results from there. And that's what we'll be doing. To set up an incremental loading consolidation specimen, we're going to take our trimmed specimen in the ring and set it up in a basin. So we're going to submerge the specimen during consolidation. There won't be any back pressure, but it will be at least underwater. And so on the bottom of this basin is a porous stone that's almost as big as the basin, bigger than the ring we're going to use. And we're going to set the specimen down on that porous stone. And then we'll have a top porous stone that's fitted to just barely fit inside the inside diameter of the ring. So it barely slides through a particular ring. Our rings are all slightly different sizes, so there are custom stones that go with each one. And we want to get that as centered as we possibly can so that when we start to push down on the specimen, the stone can pass into the inside diameter of the ring without catching on the edge. That's a big problem if it happens. But of course, if we had a larger gap around, then we would start to squeeze soft soil around the stone instead of getting one-dimensional consolidation. So that fit is very important. On top of the top porous stone, we're going to put just a brass rigid disc with a hole through the center. The centering on that is less crucial, but of course once you have a nice circle, it's not too hard to get it centered there. And the hole in the center of that circle is so that we can have our height measurement happen down on the porous stone surface. So in the old days, we would have attached a dial gauge here to the center of the specimen, and we would take manual readings of changes in height with time. But to have a computer take it, you either need a digital dial gauge, or what we're going to use is a linear variable differential transformer. And I'm seeing that I put the whole system slightly too far from the post, so I'm shifting it a little bit. So this is the LVDT. It's got two separate parts that come apart. This is a magnetic core, and this is the winding, or the housing, in which there are several windings. And so this senses the position of the core within the housing and converts that to a DC voltage reading that the computer can easily read, and then if you calibrate it, you can convert that to a reading in millimeters or inches or whatever you like. So we're going to set this up so that the LVDT is centered right through the hole in that top bronze piece. I'm going to shift the whole specimen a little more so that it's better centered. A little more. And then we're going to put this sort of frame over the top of the LVDT because we're going to need to transmit vertical load, and that's going to need to be centered as well on the bronze piece. So this is made of solid aluminum, and so as we apply load to this frame, that's going to push down on the brass disc and the porous stone without loading, because we don't want to load the LVDT. So the LVDT core is going to move down away from its housing, right, as the specimen gets shorter in an incremental consolidation test. So once it's set like this, we don't want to add water yet. We want to apply some seeding load so that there's some stress on the sample before we allow the soil to soak up water. Otherwise it may just expand and sort of lose its memory. So we're going to leave it like this, shift it over to the frame, apply some seeding load first, and then we'll add the water to the basin.